Welcome tonight to our ACM talk. We have introduction to Ray AIR for scaling AI and ML Python workloads. Speakers will be Richard, Xiaowei, and Jules of AnyScale. So about our meetup group, we're a local chapter, professional chapter of ACM, or the Association of Computing Machinery. Our meetup was founded in 1957, so a little bit older than meetup.com. We're a nonprofit to promote knowledge of modern computing. We want to create community, support networking and hiring. We're a 501c3 nonprofit run by volunteers. Our membership is only $20 a year. For our upcoming talks, check out our meetup page. And for our past talks, see our YouTube library or YouTube channel. In general, we aim for 2 monthly meetings, a general computing meeting that might be the 3rd Wednesday of the month, and a data science SIG or special interest group, typically on the 4th Monday of the month. We also like to support networking and job hiring announcements, especially in the days before COVID. Then we could have a half hour with pizza and people getting ready to sit down for networking. If you want to post any particular job openings, you can post them to the Zoom chat and others can see that. So some of our upcoming events well, tonight is the intro to Ray AIR for scaling AI and ML. The next event is Monday the 7th. So that'll be compressing deep learning models by up to 10,000 with probabilistic hash functions. So that's from a startup, Third AI. Somebody I met at a recent conference at KDD. Also,
Greg?
Yes.
We also have something coming up in beginning of the year.
Yes, there was a Ray event coming up in the beginning of the year. Does somebody want to speak to that?
Yes, I can briefly speak to it. We are in actually a planning process along with Yash to actually do an all-day workshop about Ray. And there'll be several components, several modules associated with that. We're going to be starting with how introduction to Ray. We'll be talking about how you can actually use Ray core APIs to scale your both Python workloads. And then we'll transition that into the introduction to Ray Runtime, which you're actually going to get a good intro today, both from Richard as well as from Xiaowei, about writing an end-to-end application. And this is going to be an all-day workshop. So it's in the planning, and stay tuned for the announcement in the ACA particular meetup from Yash and myself and my esteemed head of training, Kamil. It's still in the planning, so we're thinking about the last week of February. So keep in mind and do join us, because this is going to be an in-person all-day event. Everything you want to know about Ray is the place to be. So hopefully we can share all that with you, and hope you will be able to join us next year. Thank you.
Thanks. Yeah, that should be very exciting. Looking forward to that. Thank you for bringing that up. We also have a call for volunteers. You can start with a limited basis of helping out. Volunteers can join us monthly. We have a monthly planning meeting. When we get back to in person, then we'll probably get back to a dinner planning meeting. Membership services can help with online membership capabilities and functions. Some things are more publicity and marketing, not necessarily technical programming, but just helping promote events. Also, we can give some guidance on past member benefits or other things for promoting the SF-Bay ACM. If you have any questions, please post them in the chat window on Zoom. That can be questions for the speaker. My name is Greg. I'll be the moderator. I'll help out the speakers. Also, if you have technical issues or announcements of jobs or other data science events. So to introduce tonight's talk, we'll be talking about how AIR is different from existing ML platform tools like TFX, Sagemaker, and Kubeflow. We'll talk about how AIR allows you to program and scale your machine learning workloads easily, interoperability and integration points with other systems for storage and metadata needs. I'll talk about some of its cutting edge features for accelerating the machine learning lifecycle, such as data preprocessing, the last mile of data ingestion, tuning and training, serving at scale. Key takeaways will be understand how Ray AI Runtime can be used to implement scalable, programmable machine learning workflows. Learn how to pass and share data across distributed trainers and Ray native libraries. Such as tune, serve, train, rlib, and how to scale Python-based workloads. So for some backgrounds on some of our speakers, Richard is an engineering manager and a technical lead at AnyScale, where he leads a team in building open source libraries on top of Ray. He's on leave from the PhD program at UC Berkeley, where he worked in the RISE lab, advised by Ian Stoica, Joseph Gonzalez, and Ken Goldberg. In his time in the PhD program, he's part of the Ray team, building scalable ML libraries on top of Ray. Xiaowei Jiang is a senior software engineer working on the Ray OSS project, mostly focusing on machine learning libraries. Before Ray, she worked in Google Assistant for 4 years and on Uber's growth team for 2 years. Xiaowei is passionate about applying Ray to complex machine learning systems and enabling Ray users by addressing their use cases and pain points. So if we were in person, I'd say give a warm round of applause for our speakers. I'll stop sharing and turn it over to them. Thank you very much.
Cool. Thanks, Greg. I can take it over from here and just share my screen real quick. I assume my screen is looking okay. Cool.
Yes, it is.
So, okay, great. Yeah. So I'm here to tell you about Ray AIR, which is a AI runtime, and this is a scalable toolkit for end-to-end machine learning applications that was released recently with Ray 2.0. And so let me tell you let me just run through a quick couple of slides telling us about like where I'm coming from and what are the organizations that I'm part of. So I'm here representing AnyScale. AnyScale is a startup that is working on this open source project called Ray. We're the original creators of the project, and the primary focus of our company is to build a unified compute platform to develop and deploy and manage scalable AI and Python applications. And why do we do this? And the reason is because scaling is inevitable today, because machine learning and Python applications are requiring more and more compute and more data. Distributed computing is not an easy task by any means. There are PhDs, hundreds of PhDs being spent studying this particular topic, and we want to make it easier for every developer. So let me quickly also run through an overview of Ray, because I've been using that word multiple times and you probably don't know anything about it. So Ray is a simple general purpose library for distributed computing, largely targeting the Python ecosystem. It also contains an ecosystem of Python libraries for scaling machine learning and more. And finally, it runs on any sort of compute platform, including your laptop, public cloud, Kubernetes, and on-premise servers as well. So you can think of Ray as a layered cake of functionality and capabilities for scaling machine learning and Python workloads. So let's break this down a little bit. What does this layered cake mean, really, right? And so at the very bottom, right here on the very bottom of this, we basically show that Ray can run on these cloud providers, including Kubernetes, right? And in the middle there, we have these concepts called tasks, actors, and objects. And this is what we call Ray Core. Ray Core is a universal and general purpose framework providing simple primitives for writing distributed applications. And I'll dive into exactly what these primitives are. And the philosophy of this particular API is to provide, to focus on simplicity and speed. And ideally, you have, what we provide is an abstraction that takes care of all of the underlying sort of performance, scheduling, fault tolerance, memory management, so on and so forth, so that programmers can easily express their distributed application like a standard Python program instead of needing to think about a distributed program. Now, on top, what we have is two sort of layers. So, or two pillars. The first pillar is a pillar of Ray AIR, which is this AI runtime. It's actually composed of multiple native libraries built upon Ray Core, and also contains third-party ecosystem integrations that work really well with Ray. And finally, if you want to write your own distributed custom application, you can easily do so with the Ray primitives and APIs, and Ray will take care of the distributed execution, all basically for free for you. So now let's dive a little bit into just to give a little bit more color into the architecture. And so specifically the anatomy of a Ray cluster, which largely is more closer to the hardware and is abstracted away by the Ray programming APIs, is shown as follows. The key concepts here are having workers, having a scheduler and an object store and a control store. So basically a lot of the things in the head node, right? And so with it, basically when you express a driver, a Python program, that will be considered a driver, and that's the root at which your Python script exists, and it will submit Python sort of Ray tasks and Ray actors, and I'll talk about those concepts in a bit. So it will submit work to the Ray cluster. The work will be done by the workers, which are just Python processes across all the different nodes, and all the workers are managed by a daemon process called the Raylet. The Raylet also contains a local scheduler in addition to an object store, and the scheduler takes care of finding out where the work is going to get landed when you submit it from the driver, and then the object store is going to take care of the sort of the data types that get transferred across worker to worker. The object store is very cool. It's a zero copy shared memory object store within the process, and then also has sort of nice performance guarantees when sort of communicating across workers. But I'll save that sort of those details for the Ray white paper, which you can find online. And finally, there's a metadata store, the global control store, which basically keeps track of all of the references and locations of all of the Ray concepts and actors and objects and so on and so forth. Okay, so this is very much some of the very, very high level things, but I think one thing that to call out here is that, like, unlike other distributed execution systems, whether it be like an MPI or Kubernetes or Spark, there is a middle layer, this Raylet layer that is unique to Ray. And the white paper will sort of talk a little bit more about why this is so interesting. But it essentially allows us to express very, very fine-grained distributed functions and tasks in a way that that Spark and other systems cannot. And basically, it's all about performance.
Are the worker nodes always consistent in like Intel versus, they all must be Intel or they all must be GPU, or can it be heterogeneous?
Yeah, so I can let me dive right into that right here. So this sort of gives you an idea of the programming model so that we can sort of talk a little bit about how the resource management and how the resource scheduling works. So here on the left, we have a couple standard Python functions and classes, right? And the formatting is a little bit odd, but the point is that, like, you have these functions and classes. And for functions, what you can do with Ray is you can tag it with a decorator, and now it becomes a asynchronous execution, or a task. Basically, it becomes a task that gets a piece of work that gets executed in an asynchronous and distributed fashion. So you can call f.remote, which will execute f on one of the Ray cluster workers. And you can do the same with actors, right? So you can specify a class and you can tag it with the Ray.remote, and now suddenly, like, now you have a server essentially, where you can submit work and you can call methods, and the work will happen on a separate machine, on a separate process. Now, I guess to answer your question, so these are very generic Python work units, right? And they will execute by default on CPU. But let's say if you have something like PyTorch, which does GPU execution, you can also specify that within this process, like, PyTorch.init or whatever, and that will create a object on the GPU memory, and you can do GPU computation there. That being said, Ray does not automatically compile any of these functions. It basically operates within Python land only. Does that answer your question, Greg?
Yes, thank you.
Great. And finally, like what you'll notice is there's also this object store. So what that means is that we can have functions and classes, but it doesn't really matter if you can't invoke if you can't operate on data, right? And so Ray has an object store that allows you to sort of move data across the cluster really easily. So now to the meat of the talk today, what I want to sort of cover is the Ray AI Runtime, which is a scalable runtime for end-to-end applications. And we'll talk about this in a bit in much detail, but at a very high level, the Ray AI Runtime is this layer in the middle, which provides a couple libraries for doing specific machine learning related tasks. So datasets, Ray datasets will provide you a simple interface for on large data sets. Ray train will allow you to do distributed training. Ray RLib allows you to distribute reinforcement learning. Ray tune can allow you to do distributed hyperparameter tuning, and Ray serve allows you to serve your created model, your trained model at scale. And again, I'll cover more of this in detail, but at a very high level, it's a collection of different libraries that integrate with the rest of the ecosystem transparently, and also is built upon the Ray core abstractions, allowing us to build these scalable libraries easily. So let me quickly give a project overview for Ray AI. The Ray team has worked with machine learning users and infra groups at very large, very many companies, including Uber and Shopify, Cruise, OpenAI for several years now. And this new project, Ray AI, is an effort to synthesize these lessons into a simple toolkit for the community. It's built on top of these libraries that I just talked about. It provides a unified API for end-to-end machine learning with the express goal of simplifying existing machine learning infrastructure. So for the people who are on the call today, you may sort of be wondering, what does it mean to simplify machine learning infrastructure, right? So let me tell you a little bit.
Question from the audience, and maybe this is something you'll get to in an upcoming slide, so if you want to delay answering, but they ask, what is the difference between Ray core, train, tune, serve, and Ray AI?
Yeah, that's a great question. So Ray core is the underlying primitives that I showed you. We'll then talk about Ray AI, which is basically a collection of libraries. And train, tune, and serve, they are the libraries that compose Ray AI, right? So Ray AI is sort of like, you can think of it like the Adobe Essential Suite, whereas like Photoshop is one of these components within the suite. And in the Ray equivalent, like Ray train or like Ray serve would be the Photoshop within the Ray AI suite of libraries. And again, all of these libraries are built on top of Ray core, which are like which is the thing that I showed you earlier with like the decorator and the functions and classes.
Okay, thank you.
Yep. So let me talk about some of the challenges and so why this project exists in the first place, right? So one of the key challenges that we're seeing is that it's still not easy to take machine learning from development to production at scale. On the right hand side of the screen, you see that we have an everyday training process from many common sort of machine learning pipelines in the industry. And even with this simple bit, so basically what's happening in this particular graph is like you have a distributed system for doing pre-processing. You have a distributed system which generates training and validation data. Then you have a distributed system for doing training, which then creates a model. And then you have another distributed system for doing evaluation. And that sort of does batch inference on top of them with the model that's being created. Now, what you're seeing here is actually 4 different distributed systems that need to be stitched together just for a very standard machine learning workload. And this introduces a crap ton of operational overhead. So on top of that, the machine learning field moves extremely quickly. So your infrastructure often goes out of date, forcing painful migrations. So let's dive into this a little bit more. There's basically 3 problems that are at play. First of all, scaling is hard, right? So that's why we have these distributed systems in the first place. Like it's not easy it's important to scale, but it's not easy to do so because you have to work with these distributed systems. And this is especially not nice if you're a data scientist and want to focus on just standard modeling machine learning. Now, platform solutions are a way of addressing this problem, but as you might know, platform solutions such as Sagemaker and similar to that will limit your flexibility because the field is changing rapidly and you don't necessarily get the best features from these platforms. But this is a catch-22 because if you don't have a common platform, then you have to build your own stuff, and building out your own distributed system from scratch is really time-consuming. It's out of reach for most organizations. And so basically, the common challenge here comes from the need to scale out your machine learning infrastructure and need to go from, especially from development to production. To understand this, let's travel back in time a decade ago, where we were all working on a single machine and data was just a couple files and you could easily run machine learning scripts on your laptop. These problems were really easy to tackle, right? Now, with Ray and Ray AI especially, we're trying to bring a similar experience back to the machine learning practitioners in today's landscape. We're working with a huge amount of data with a huge amount of models. Machine learning is much more powerful nowadays, but it's still like the ecosystem is so much more broader. What resonates with our users that we've worked with in the wild is the ability to express these sort of distributed machine learning pipelines or applications with just a single Python script using the best in-class libraries. For example, you might want to leverage some of the data libraries or machine learning libraries for pre-processing and training, and then you have some other set of machine learning like scoring libraries or serving libraries that you want to stitch together and scale out. And this is possible with Ray because Ray allows, the power of Ray is that it enables distributed computation to be composed with just code. And as a result, your developers feel instantly much more productive and you get much greater performance. So let's go on to the next slide here. So let's talk about Ray AI. What is it exactly, right? So now that we all understand sort of the problem at hand, Ray AI Runtime, or AIR for short, is a scalable toolkit for end-to-end machine learning applications. It's built on Ray Core, as we mentioned earlier, which provides flexible and open support for machine learning compute from end to end. Right, and it focuses specifically on compute and leverages integrations for storage and tracking. Ray AI also has these libraries that make it easy to scale certain workloads for data scientists and machine learning engineers. The unified API that we'll sort of talk about very soon allows these libraries to work seamlessly with each other and also integrate nicely with the rapidly growing ecosystem. So let me talk a little bit about why it's important to have this library there, right? Especially to have scalable libraries. So with non-scalable libraries, there can be a high friction handoff between going from development to going to production, right? And so essentially what you have here is like, you might have a data science team that's like really working on their modeling stuff and applying their genius there. But as soon as they want to go to production, they have to sort of scale out, right? They have to sort of, they have to work with larger amounts of data and they enter this production environment and suddenly they have to rewrite all their code because the production environment has these opinionated libraries or distributed systems, and it doesn't work well with the existing set of libraries that you have. So ideally, you actually have a very seamless handoff between dev and production, right? Ideally, you have scalable libraries that are easy for data scientists to pick up, but you can use the same infrastructure within both the development and production environment, allowing you to improve productivity for your entire team.
A question.
So finally,
on your slide, there's so many different software icons. And so, no, go back. Yeah, this one. So there's so many different versions. So like if you have a TensorFlow of a certain version that's compatible with a scikit-learn of a certain version, which is compatible with something else of a certain version. So there's this alignment you have to do mechanically. So if a data scientist may want to use this latest architecture that's uses a new version of TensorFlow, but then the software engineering infrastructure hasn't caught up to the latest version of everything. There's a big challenge logistically sometimes, especially if you're managing multiple enterprise applications. Do you?
Yeah, absolutely. Sorry, go ahead.
Yeah, is there much infrastructure that you have that you can say, gee, for this enterprise app A, we're going to have everything aligned around TensorFlow version something. For this enterprise app, something else, then we're aligning around whatever works for Spark version A, something like that. Or how do you handle that? Because getting everything to be compatible with each other in the versions.
Yeah, so that's a good question. So so essentially, like, there's two answers to this. One is that, like, with Ray, we aim to provide this like layer it's kind of like a hub, right? So what ideally you can do is you have like different windows of, you have as broad of a window for supporting any of these libraries, so that you don't introduce unnecessary bounds or constraints on each particular integration. Now, in terms of when you actually go into production and take your workload to production, the challenge there is going to be, how do you express like your how do you sort of resolve the constraints and make sure you have the right dependencies, right? And so for that, obviously Ray will run fine on Docker, and you can bundle your dependencies there and have a different Docker image for every application. But Ray also provides runtime environments, like a feature called runtime environments, where you can express exactly what the type of dependency and what version of the dependency you want for your application, allowing like sort of greater flexibility. It could be a blessing or a curse, but it provides some amount of flexibility for you to be very explicit about what libraries your application should run with.
Thank you. Yeah, that's a tangled mess sometimes, so it's good to understand how you deal with that.
Absolutely. So let's quickly talk about integrations, right? So this is one of the biggest parts of the machine learning ecosystem. It doesn't really, like, if your library doesn't integrate with anything, then it may as well just exist within within the box. But Ray does provide built-in integrations for some of the most popular frameworks. So, for example, if you want to use Ray AIR with PyTorch, there is a PyTorch trainer that allows you to scale PyTorch transparently. Same with TensorFlow, same with Hugging Face, same with XGBoost, so on and so forth. Ray AIR also provides an integration API to easily add new integrations. And since Ray AIR is built on Ray Core, you can also build custom scalable components. If you find that, like, your integration story, and if you find that there's things that are missing within the ecosystem and you still need things to scale, then you can build your own. So overall, Ray AIR aims to simplify scalable machine learning infrastructure. Scaling is made easy with Ray so that you can scale from development to production with the same code. Ray AIR provides a unified API for scalable integrations, meaning that you can choose the best, your favorite ecosystem libraries. And finally, Ray AIR can handle machine learning workflows end-to-end with Ray, so that you can focus on one production system instead of hundreds or dozens. So when would you use Ray AIR? So you can use Ray AIR. You don't need to use all of the libraries at once. The nice thing about Ray AIR is we sort of thought about, like, what are the different sort of experiences that people want to do. And so here's 4 different categories, right? You can use it to scale a single type of workload, whether it be like distributed training or batch prediction, without needing to buy into the entire toolkit. You can build end-to-end scalable machine learning applications using Ray AIR. Ray AIR makes it easy to plug and play new tools from the ecosystem using interfaces such as Trainer or Tuner, which we'll talk about more in later. And finally, you can use Ray AIR as a compute layer to build your own custom machine learning platform, should you choose to do so. Again, you don't need to do all of this. You can choose one. And I'll talk about some of the concrete examples of these quadrants in the second half of the talk. Right. Again, this is just like sort of sharing a little bit more about, like, where Ray AIR can be used. It's for the entire machine learning organization. For data scientists, it allows people to easily express scalable workloads. And for machine learning engineers, it provides unified platform abstractions to easily onboard and integrate necessary tooling. So Ray AI is a scalable and unified toolkit for both of these roles, data scientist or machine learning engineer. Right. Okay, so let's now dive into the meat of Ray AI, right? What comes out of the box with AIR? You have data processing, you have training, you have tuning, batch prediction, and serving. We'll talk a little bit about each. So Ray datasets provide scalable data preparation, pre-processing, and loading. Datasets is specifically, it's a library that's built for machine learning tasks, right? You have like these preprocessors that help handle the data, and you can also pass the data set into a trainer, which we'll talk about next, to seamlessly load data in a distributed fashion from megabyte to terabyte scale. And these preprocessors provide also a nice experience because you can express it once and you can use it across both training and inference. There's a question in that I'll answer right now, which is, it looks like Ray AI is a high-level library. In what situations will I use Ray Core? Can I use both Ray AI and Ray Core together? And the answer is in situations where Ray AI does not capture your workload properly, then you can use Ray Core to scale your workloads. In particular, Ray Core is more focused on general Python rather than machine learning. So you can, if you have any distributed Python tasks that you want to do, or you have some sort of task that you happen to be using Python, right? Then you should use Ray Core. If Ray AI doesn't provide already the necessary functionality for you. And can you use both Ray AI and Ray Core together? Yeah, you can certainly do that within the same application. Great. Hope that answered your question. Let's move on. Now the next thing is about model training, right? So after you've created a data set, you can pass it into, you can use a trainer to load that data at scale and then also do distributed training. And it's a single API that runs most of the popular machine learning training frameworks, including Hugging Face, XGBoost, and so on and so forth, with seamless integration with other Ray AI libraries. So in addition to this, one thing that we offer is this tuner interface, which performs scalable hyperparameter tuning. So for this, you can basically in the trainer, and you can run multiple concurrent training jobs, allowing you to easily tune your trainer and tune your hyperparameters of your model that you're trying to train, and provides cutting edge optimization algorithms, and also provides a fault tolerance at scale. So if you have if you're running on spot instances and one of the node dies, then this tuner will sort of automatically restart it for you. The other thing that I want to call out here is that it's oftentimes now that you have to do distributed training where your model is so big and your data is so big that you have to go across multiple nodes. You can do that in conjunction with Ray Tune, so you can do multiple levels of parallelism easily. And so that becomes a very, very powerful feature for a lot of users. Finally, there's the scalable batch prediction, which provides a interface for training, or sorry, for taking the trained model and applying it across a large data set. It executes inference on distributed data using CPUs or GPUs, and you can bring your own model or load from existing checkpoints. So together, all those four libraries sort of compose the offline workloads. In addition, Ray has a library called Ray Serve, which provides scalable online inference. And so you can just deploy these models that you've generated as a inference service in Ray, and you can also compose multiple models together into a pipeline with custom business logic. Okay, so that's very much the high level of how the Ray AI, the libraries within Ray AI. Then let's talk about a little bit about how you would use it in practice. So we'll walk through all four of these situations, but I'll do so rather quickly so that we can actually get to a demo of how you would use Ray AI in practice. So let's talk about using Ray AI for a single workload, right? Let's say you have a machine learning pipeline already, you only want to replace batch prediction. And so again, the message to take here is that Ray AIR does not require you to rip out your entire pipeline. You can do this in a piecemeal fashion. And so in 29 lines of code, I'll show you how you might do this with Ray. So here on the screen, we have a pre-trained model and cloud storage API or URL. We'll create a Ray dataset by reading from this data source and passing in the data URL. We'll create a checkpoint from the given model that I constructed above, and I'll pass that checkpoint as a carrier into this batch predictor. And then I'll call predict on the data set that I just created from the S3 bucket. So what's not shown here is that Ray will automatically scale out the number of workers and scale up the cluster size if necessary. You can also use GPUs to do prediction here. Finally, you can write the outputs back to S3. So what we demonstrated just now is a really simple way of expressing this batch prediction job. And in addition, if you're running it within a machine learning pipeline, you may want to also add some logic to start up or shut down your Ray cluster, right? Now, compared to another solution like Sagemaker, Ray AIR actually removes a lot of unnecessary complexity. Like Sagemaker, batch inference requires you to create an Airflow DAG for some reason, create a Docker image, then test locally, then push the Docker image to ECR, then like partition the work across all the machines, and then copy all the S3 files manually, and so on and so forth. It's actually very, very complicated. So that is all to say that even if you choose to just use a single part of the Ray AIR library, you can do so basically and create a massive reduction in complexity within your application or your pipeline, thereby boosting developer productivity. Let's talk about what happens if you want to replace, you're a bit more ambitious and you want to replace more of your machine learning workflow. So let's do like the entire data processing, training, tuning, batch prediction all in Ray. So effectively here you have the high level code snippet of what you might do for data processing, where the first line is we're loading a CSV from some custom location, and then we'll generate a training and validation data set. And then we'll also create a preprocessor. This is from Ray data for normalizing a given column, and we'll do so in the distributed fashion automatically. We'll pass in, we'll create a trainer. In this example, we'll use XGBoost trainer, and we specify, how many workers we want to use, what's the target of the data set, what's like the predictive value, what the values that we want to predict, and what's the data sets that we want to pass in addition to the preprocessor. So we'll be running. Once you call trainer.fit, you'll execute the training in a distributed fashion. You see, we get here a result object. Another thing that you can do is pass in the entire trainer, and you can tune across a particular parameter that you want to do, right? So it could be like max depth or something like that, and you can specify how many samples you want to do. And from you can fetch a checkpoint. And this checkpoint then can be passed into the batch predictor that we saw from just earlier, which will do batch prediction or batch inference in a scalable fashion. And so there you have it. This is a full end-to-end machine learning workflow at scale with just around 20 something lines of code. And if you were to do this in practice, like this is very, very close to what the API would look like, maybe modulo some import statements. The other thing that's very cool about this and specifically is the scalability, right? So you can easily make this scale. You can just change a couple of parameters to increase the amount of parallelism on both training and tuning, right? So that's one of the powerful aspects of Ray AIR. So finally, or I guess the next use case we want to talk about is integration into your machine learning ecosystem, right? And so if you're a machine learning team, what I have here is probably something that you're very familiar with. It's the huge, the rapidly evolving machine learning field with all these different ML ops tools and so on and so forth. The nice thing about Ray AIR is that it also already provides a large number of integrations with the open source ecosystem. There's a ton of logos on this page, but just to cut it short, Ray AI actually has integrations with the data ecosystems such as pandas and NumPy, integrations with common machine learning frameworks such as scikit-learn, TensorFlow, and PyTorch, optimization libraries such as Optuna and HyperOpt, model monitoring, integration with model monitoring services such as MLflow or weights and biases or Arise, and also integration with model serving libraries such as FastAPI. But this is not all. This is obviously this is a good start. But one thing that I want to call out is that it also provides integration APIs to plug in new ecosystem libraries, right? And specifically, you can sort of, this is really nice because with all these different integration APIs, you can plug and play new machine learning frameworks or new data sources or new services so that you can stay ahead of the curve and you don't need to refactor your entire machine learning platform or whatever system that you have in order to support just yet another service. Yeah, so effectively what we see here is because Ray AI is so flexible in terms of its ecosystem strategy, allows you to remain future-proof for your machine learning platform. There's a question from Ling Yi. Is there any integration of a high-performance inference server like Triton with Ray Serve? This is a great question. And specifically, answer is right now no, but the team is actively investigating this. What I would say is that at the end of the day, it should be very easy to do. And if you can open a GitHub pull, or sorry, not GitHub pull request, GitHub issue, just expressing your interest in this particular integration, this would be really good for us to know, collect signal from the community.
A question: many times when you roll out a new model to replace an existing model doing the same function, there's a champion challenger test. So I assume you would just implement something in one of these workflow boxes just to kind of compare the distribution. Like if you want to score the new model with 1% of the records randomly, and then later on you go up to 10% and things like that.
Yeah, that's exactly right. So like you would just leverage the batch prediction module, which would allow for scalable scoring with like 10, 20 lines of code. And you can just write a simple module above that to do the champion tournament.
And things are mostly in batch, or is there support for streaming or like headless Lambda servers that could be lower cost in the cloud?
So right now the support is largely on batch. That being said, Ray clusters are auto scaling, so they can provision and deprovision nodes very, very quickly. Thereby, oftentimes actually reducing your cost of ownership compared to Lambdas. In terms of streaming, so we are working on the functionality called basically data pipelining. So effectively, you can ingest data from a data source and leverage less memory than needing to load all the memory into data, loading all the data into memory. It does not have like the same streaming guarantees, like the exactly once guarantees that is something like Kafka might have. But as far as I can tell, like if you want to integrate this into like a streaming system or connect the two together, it should be possible. And I'd love to chat with you more if you're interested in doing that.
Yeah, I was thinking Kafka would probably be an infrastructure that could be leveraged for that.
Right, exactly. So yeah, so the last thing I want to talk a little bit about is like using Ray AI as part of your the core part of your machine learning platform, right? Let's say you have some platform that you're building. So let me just quickly talk about a similar architecture that is currently happening at Shopify. So Shopify is using a lot of these Ray AI libraries. And what they're doing is they're actually leveraging a Ray AI solely for compute, right? And effectively, and these sort of different libraries that they're using, including training, batch inference, preprocessing, and so on and so forth. But Ray is only one part of their machine learning platform. It also includes, other parts like a feature store, a data lake, orchestrators, Jupyter notebooks, and so on and so forth. And it's basically only one part. So I think what I want to do next is I want to really break this down into sort of, like, what does this really mean, right? And so I think from the user perspective, we've walked through a couple of Ray AI example programs. And so we'll start here. It's just a standard Python program. You'll run it like Python, like you can execute it with like Python script.py, right? What happens if you have a platform is you have multiple users that want to do this. And so in order to support multiple users, you probably want to have a cluster scheduling mechanism, which can be either Anyscale, which is the the company that I represent, which provides a really seamless experience around managed Ray clusters, or with Kubernetes, which is a integration with Kubernetes. Each of these programs will probably interact with other components such as feature stores, lakehouse, experiment tracking mechanisms, so on and so forth. And also, on the other hand, from the user interface perspective, you want users to interact with the platform, so you have like a notebook service or a job scheduler. Notice that like all this stuff is outside of Ray AI, but Ray AI integrates seamlessly with them. And this is sort of the architecture that people are putting it together within the community. So again, Ray AI is like the compute core for your machine learning platform, but it would be unwise to say this is the only part of your machine learning platform. So the current status, let's quickly talk about Ray AI itself, right? What's the current status? What's going on? So right now it's released as a beta project. In the future release, we plan to add more integration, better support for like these sort of pipeline use cases, similar to what you were describing there, Greg, when you don't need to load everything into memory, and also improve scalability and performance benchmarks for these data intensive use cases. And I think one thing to call out is that like, even though it's a beta project, I think a lot of users are super excited. So for example, like one data scientist from a large music streaming company has mentioned to me that like he feels as if like his productivity has at least doubled, if not more. He's using that nightly builds, and this is previous to Ray AI being released, and it's been such a massive productivity boost for him. Another machine learning engineer has mentioned that the Ray AI has greatly improved the developer experience, and within 2 weeks was able to outperform a data ingest pipeline that he built by hand over 6 months. Right. So what we're seeing here is that like, and this is not all that we're hearing this across multiple users. This is a basically experience that like I think could really revolutionize how you're doing data science and how you're moving into production within your organization. If you're interested in learning more, we can sort of sorry, I have I guess like the wrong slide here, but yeah, come chat with us on the Ray Slack. And I think what we'll do now is I think Xiaowei will do a demo about that exactly what Ray AI provides and how you might actually get this working on a cluster. I guess before that, are there any questions? Maybe people want to answer on the Q&A.
Sounds very exciting so far. Good work.
Cool. Okay. Xiaowei, I'll let you take it.
Cool. Thanks, Richard. Can you guys all see my screen?
Yep.
Cool. Okay, so while Richard is presenting, I already started a Ray cluster. So which consists of 2 nodes, one head node, one worker node, and we can easily access the Ray cluster status through the CLI command Ray status. Yeah, as you can see, like these are the nodes presented here. Yeah, one thing I want to note is like each node has 4 GPUs. So altogether we have 8 GPUs for our Ray cluster. So now that we have our Ray cluster ready, so now let's walk through one example to showcase how we can use Ray AI Runtime, also known as AIR, to build scalable machine learning applications. So as Richard has said, so Ray
Xiaowei, can you zoom in a little bit more?
Oh,
Maybe,
sorry.
yeah.
Is it too small? Is it better now?
Yeah, it's good.
Cool. Okay, so as Richard has mentioned, so there are several components that Ray AI offers. So let's go over them again. So there are like Ray data library for data ingestion and pre-processing. There's a Ray training for distributed training, Ray tune for distributed tuning, and for batch prediction, we have Ray batch predictor, and for serving, we have Ray serve. So we want to showcase how to write Ray AI applications to showcase each single of this component box drawn here. So this notebook, we will walk you through a CFAR10 dataset for image classification. And so for this dataset, I'm sure like everybody is pretty much familiar with it. So it has like a bunch of 32 by 32 colorful images in 10 classes. And it has 50K training images and 10K test images. This is just some sample images for some random images from each category here. So let's make sure we have all the correct imports here. And now let's connect to the Ray cluster we have just started. So as you can see, like we can inspect our cluster from the ray.cluster resources, and it shows the correct number of GPU resources we have, and also like we have 2 nodes as listed here. Okay, so as a first step, we want to show how do you get data into the Ray clusters through a Ray dataset. So here we show that using a simple torch data source, which is just for demo purposes. It doesn't support parallel reads. For more serious workloads, one may refer to Ray data input formats as linked here to see some of the supported formats for scalable parallel reads. So one thing to note is, as Richard has mentioned, the Ray cluster has this notion of abstraction of object store. So when we say we get a data set loaded into Ray cluster, what we mean is it is stored into the Ray object store, which is a shared memory layer across all the nodes in the cluster, so that all the downstream ML tasks, for example, different workers on different nodes, can access the data set easily without user having to care about the distributed nature of it. So let me just quickly launch this few cells here. Yeah, so as it's reading, we can, yeah, it may take some time, but let's look at step number 2. So that step number 1 is to get the CFAR10 set into Ray cluster. So the step number 2 is we want to showcase how to create a preprocessor to transform the data. So as you can see, like here, the schema is like class tuple. What we really want is to convert it into a NumPy format so that it can be easily accessed by all the distributed workers downstream using iter-torch batches we'll show later. And to do this transformation, we can use the Ray dataset API called map batches to convert. So this is just to showcase how we can use a UDF, which is user-defined function, to apply it to every single row of the data set. So as you can see, after the transformation, the schema is changed to a dictionary of image and label, and with image being like a NumPy format. So I do want to mention, like, this is sort of a like special case, but for like tabular data for other pre-processing needs, for example, scaling, normalizing, or like one-hot encoding, Ray AI provides a host or a collection of preprocessors one can choose from. So I also linked the preprocessor here that can be supplied downstream to trainers, as well as batch predictions for consistency. So as you can see, like after basically the data set, we have like 50K for training and then 10K for testing data set. So now that we have the data set prepared, like ingested and prepared, we want to proceed to training and tuning. And to do that, I want to just quickly go over the trainer API again. So we offer integrations into various popular machine learning frameworks, including Torch or TensorFlow. So here, since we're doing this task, we showcase using Torch Trainer. Yeah, so I think maybe the most important thing to note here is this training function that needs to be fed into the Torch Trainer. Maybe it's interesting to showcase how exactly can we write this training function. So at first glance, it's actually pretty much similar to what you would write for a Torch DDP training function, with just a few things I want to highlight here. So for example, so here, like to move the model to the GPU instance we have, I think the Ray Train library has this prepare model utility function that can easily achieve that. Another thing I want to point out is this modification, like we can easily access each batch using iterTorch batches, and the result coming out of it is basically just very easily like a usable Torch tensor format that you can basically do the rest, like the training forward and backward and optimization steps. And another thing I want to point out is like basically we want to report some metrics into back to the Ray system. So this is like the metrics we report the training loss here, and then we can report it using the session API as shown here. And we will come back to basically when we train and tune the model, we'll see from the console output how this metric is being updated as iteration goes on. So let's go back. So with this is probably the most important argument into the constructor of trainer. Of course, we also want to specify the train data set here. Another thing very interesting is, like, as Richard mentioned, like the scalability story here. So basically, remember I said we have like a 2-node cluster and each node has 4 GPUs. So the setup here is for each trainer to consume 4 GPUs. Basically, each trainer will have 4 distributed workers, and each distributed worker will consume 1 GPU. So one can easily specify that by this scaling config and just feed into number of workers equal to 4 and use GPU equals to true. So if you only want to do a training job, so with this trainer, you can just call trainer. So you can just call trainer.fit after this, and you will be launching 1 training job. But since we also want to kind of showcase tuning, so I'm gonna just continue with how we can easily have like specify a hyperparameter tuning job with the trainer that we just created here. So so for example, one can easily using the tuner API, one can easily stick in the trainer here together with some definition of the search space, which we call param space here. One can also specify state-of-the-art search algorithms and schedulers, which is not shown here for simplicity. So for this example, we will showcase a simple grid search with basically just searching over a different learning rate here. Yeah, so for more like advanced tuning setup, one may want to specify, for example, search algorithm, for example, Optuna, or like more advanced scheduling algorithm, for example, population-based training, or ASHA, which is like early stopping policies here. Okay, so let's say we have this tuner specified as well. So let's let it run for a while and see what the result look like. So
do you have
yeah.
data-driven ways of stopping the training when you see kind of like a comparison between the training and a test set or tuning set?
Oh yeah, so yeah, you can interrupt with the training at any time. Basically, what we do is like we store per iteration or per epoch, we will store a checkpoint. And so say if you notice like some of the trial is like not very promising, I guess right now our API is not very flexible. What we can do now is basically kind of stop the whole thing, and you can restore from some of the more like a promising subset of like trials you may want to continue with. But there's also another API called Tune Server that allows you to interactively queue some of the bad trials as you observe them. And then so that to trim down the search space and then release the resources for maybe, yeah, basically for other new trials to new sample points to try. So those are, yeah, those are some of the.
If you're doing a neural architecture search, do you find it's better to train on like 8 GPUs at once and finish that job before you train the next one, or train 8 jobs each on one GPU and it takes longer, but then you get a wider distribution?
Oh, I see. So that depends, and depends on the nature of like each trial. And also like I use a static, basically for demo, I only use a static Ray cluster here. But ideally, you would want to maybe kind of want your a cluster to scale up as well, so that you can allow for more parallelism, not just like one by one.
Correct.
Yeah, so I think I didn't show this part, but the Ray class open source Ray has like a Ray cluster launcher that allows you to specify kind of the minimal number of workers you want to launch your Ray cluster with, and the maximum number of workers, so that you don't just burn your wallet. So those are some of the interesting APIs to look into for launching, how to kind of launch a Ray cluster in open source. For this demo, I sort of shortcutted. I use a kind of basically Anyscale, which is a managed Ray cluster version. Which is like all managed for me, and I get better monitoring and stuff. But yeah, but basic things can also be done using the open source version of Ray cluster launcher. So yeah. So as we speak, I think we already made progress into maybe a few iterations. I just want to point out like a few interesting things maybe to notice here. So for example, like this is some basic status. And interesting thing about system information maybe is like we are basically occupying all the 8 GPUs, and yeah, and then we can do to see maybe, yeah, basically we have like a pretty good GPU utilization here. Yeah, so, and also basically we're also listing out the trial status and basically what epochs they are on, which nodes they are the trial is running on, and so like some, yeah, this train loss is what I show in the kind of this is a session.report metrics. So this metrics is what is being shown here as the train loss. This is also would be the kind of same metric that if you're using tuning and kind of do some early pruning and things like that, this will be kind of the criteria to look at.
There were a couple of audience questions. One was when to use the Ray cluster and when to use KubeArray. What's the difference?
Oh, right. So I would say for Ray cluster, it has pretty good integration into like the public cloud. For example, like you can search for examples in our documentation. It has a way to, for example, launch into AWS, launch into GCP and things like that. So those are like when to use the open source Ray cluster launcher. And for the Kubernetes, I guess it's like if you have your own Kubernetes cluster, and then yeah, you want to launch Ray cluster on top of it. That's when to use like Kubernetes.
Okay. And then another question is, do we currently enforce the resource constraints for data loader and Ray? So such as the number of CPU per GPU worker for the data loader?
Yeah, that is sort of pretty vague right now. I think we are still shaping up that story here. Like how exactly to kind of define the resources for the data part of the story. But I think the data team is on it right now. Yeah. Maybe
Okay.
yeah, maybe I can follow up with more details after getting some context from them. But I think they're working on this.
And then a question from me, a lot of times when we're doing image by image analysis, it's not just what happens at that image, but if we do object tracking over many frames, like a person walking across the screen, then they walk behind a telephone pole, they're not detected for a frame, and then they're picked up again. So the object tracking, as long as we're tracking the same alert event, what we care about is at the user level metrics as opposed to the frame level. And so if we do post-processing and we're executing object tracking over many frames, there's different object tracking algorithms. So I assume you have the same way you can do pre-processing, you can do post-processing.
Oh yeah, that's a good point. Like this is not like a example that we particularly look at, but I think it definitely it's doable to be built on top of the AIR. I don't think it's like fundamentally different. Like probably it will be more challenging technically, but I think it can be kind of modeled through like the same kind of mental model.
Okay, thank you.
Okay, cool. So I'm not gonna wait for it to finish, which I probably said like 40 iterations. So, but I think the idea is like basically, yeah, as you can see, of course, some hyperparameter yields better result than others. So let's just kill it.
And do you have a turkey in the oven, one that's already trained?
Yeah, that's the point. Yeah. Okay, it's killed. So okay, so it's killed. Let's just move on. So if it's now killed, and let's say it's kind of finished, we can just get a best checkpoint using this API. But since like we don't want to wait for it, so I already have the best checkpoint actually saved here before the demo. So this is also a good chance for me to showcase how you can just use Ray AI in a piecemeal fashion instead of like all in one kind of like all in one kind of flow. So you can just load the checkpoints this way. And then you can do best checkpoint equal to checkpoint from directory, which is like AIR kind of way of loading checkpoint from a directory. So we can do this. Let's see if okay it works. And so this will be exactly the same thing as if what we would get if we continue with the tuning and get the thing from this statement. So let's just continue on from here. So for the next step, I want to show how we can use this checkpoint object we obtained from tuning/training and use it in a batch inference scenario. So basically, yeah, so let me walk you through the API of batch predict so we do that through batch predictor API. So of course we need to specify what is the checkpoint, which is just the checkpoint we just obtained. For the predictor class, it's torch predictor. And yeah, this is my model definition. And then of course we want to say use GPU equals to true. And then we can simply call batch predictor dot predict. And just one thing to note is don't forget to specify this number of GPU per worker. So after doing this, yeah, it may, yeah, we have 10K. It should be pretty fast. Oh. Oh, I see. Let me see what's going on. Maybe it's like when I kill the cluster. Yeah, I think maybe some of the resources are not really released yet. Yeah, so basically what this message is saying is like yeah, it's basically saying I want to find a GPU to use, but as you can see here, all the GPUs are occupied, which should not be the case, but I guess it's because I forcefully killed my last execution, which caused this. So let me just try killing some of the, yeah. Maybe I will try kill. And then let me see if this can give me some of the free GPUs, and let me try this again. Okay, let me stop this. Okay, so I don't want to wait for it. As we know, live demo will always find something interesting, but
That's how we know it's live.
wait, it should be working. Oh, it's still complaining, not finding the right, which is weird. Okay, why don't I just start the kernel all over? And for that, I have to redo my import, redo my cluster initiation. And probably I need to just redo my test data set. And then just so that we have something to do batch prediction on. See, yeah, seems to be working. And let me, maybe I have to reload my best checkpoint. And let's try it again. If it doesn't work this time, I will have another, oh, it works, great. Cool. I guess, yeah, it finishes and the output is here. And let's just run through some, basically score, calculate the prediction scores and see what is the total accuracy. Oh, here. So it's not bad. Like for maybe only 10 minutes of training, or tuning, it's like 81% of accuracy. Okay, cool. So this is like batch prediction. So up to now, I think everything is about offline. But the last component I want to show is like how we can do like online prediction. So so this is done through mainly through this predictor deployment API. And yeah, and basically we can specify the number of replicas. Here is I specified as 2. Yeah, of course, we also have to give it what basically this checkpoint that we have just saved and loaded. The model definition here as well, and some basically conversion functions. So let's start this server, which may take, should be pretty fast. Okay. Okay, cool. So then we run through some, basically this is just to run through the first 10 images in the test data set and send it to the API server and see what is like the prediction result we get. So yeah, so the image is kind of blurry, but yeah, you get the idea. Yeah, so pretty much like every single case is like matched. Yeah, so this is the demo. Hopefully give you an idea of like how the various components of a machine learning pipeline can be constructed by Ray AI APIs and how they can work together. And for example, how checkpoint is the output of training and tuning, and how the same checkpoint is used for batch prediction and online survey. Yeah, so there are some additional resources linked here for people for reference. So that's it.
I assume after you have the model training and you validate it, it's gone for enough epochs. Then if you want to do some optimization so it runs faster before you go into production, then you just may have another execution block to do the quantization or pruning or whatever else you want to do.
Yeah. If you want to do that, it's just not showcased here. Yeah.
Sure. Yeah, that's fine. Yeah, I wasn't expecting every feature to be shown, but just to understand where things plug in.
Yes. Yeah, that's correct. Yeah. Okay, I would stop share here.
Other questions from the audience? You can type in the Q&A or the chat window.
I did put a link in for the notebook, so people can actually look at it as well.
Okay, any concluding remarks y'all might want to make? I think y'all, looks like y'all have done quite a bit of presentation here. And
one question sometimes audience members ask if they could get a copy of the slides. If that's something you can print a PDF on the meetup site for this event, there's at the bottom, there's a comment section. If you can just put a link to the PDF for the slides. Many times people like to come back after the fact and find the slides. So if you're open to that, that would be something people would appreciate.
Yeah, I'll send you guys the PDF version of the slides, and also the link to the notebook that Xiaowei actually showed that gives you a complete end-to-end. So yeah, we'll send you that.
Yeah, that'd be great. Yeah, just on the meetup site in that comment section at the bottom, then put any links, and there's multiple discussion sections that can be posted. So whatever seems appropriate that you'd like to share.
Sure. Yeah, thanks a lot, Richard and Xiaowei. That was end-to-end demo of our Ray AI, and looking forward for the workshop in a couple of months.
There's a question that came up in the Q&A.
Mhm.
Is Ray cluster, is that a stateful deployment? For the Ray serve, is it stateful or stateless?
Yeah, so I can answer that question. So the Ray cluster is a stateful deployment. Ray serve can be a stateful deployment because it's all Python, but a lot of people just deploy it as stateless so that you have like workers that can go up and down without any worry.
Okay. Okay, well, I think we can go ahead and stop the YouTube streaming. And it looks like we've answered all the questions. Thank you, everybody, for your well-prepared presentation and good content. It looks like a good product. So hopefully we can see more details in February.
Cool.
Okay, we're looking forward. Thank you very much.
Yes, let us know how we can support you and help you be successful.
Okay, thank you.
Thank you.